All right. Today we are going to look at 1.6b, which is on page 108.
We have one student from every classroom go down to 107 to pick up a box of apples. One student from every classroom go down to 107 to pick up a box of apples.
So today we're going to start on page 108, scientific notation. If you've already done scientific notation and you feel pretty good about it, you can work ahead as we're going on. We're also going to be looking at significant figures in the context of scientific notation. So if you were away yesterday and if you have not done significant figures in physics yet, I'm going to do just a brief recap of what significant figures are like, okay? Significant figures, so for the rest of you, you can just chill out for a moment. Significant figures are all the meaningful digits in a measurement. And don't worry about copying this down because it is in the thing that you're going to watch for homework, okay? It's all the meaningful digits in a measurement. And last day we learned the little mnemonic device, NYM, okay, NIM, which stands for no, yes, and maybe. Because one of the things we're going to do with significant figures is I'm going to give you a number, maybe like 0.00580030, and I'm going to say how many significant figures are in that number, okay? The easiest part of sig figs is non-zero digits. Non-zero digits are always significant. So if I look at the 5 is significant. If I look at the 8 is significant, and the 3 is significant. Those are all non-zero digits. And I get tired of writing the word significant, so I'm just going to write sig. They are significant. Zeros are more complicated. Yesterday we learned a rule. This is the NIM rule, and those are for zeros on the left. We also have zeros in the middle, which would be like in between non-zero digits, and we also have zeros on the right of non-zero digits, off to the right of the number, and those ones are maybe. So last day we learned the rule no, yes, maybe. And so we're all going to review that with each other. So we're going to start by pointing over to your thank you so much. Would you guys like an apple? Go help yourself to an apple. Or two. Don't be shy, lots of apples. So at any rate, no, yes, maybe. You're going to do this with me. You're going to use your voice so that you engage the vocal neurons. You're going to use your hand so you involve your motion neurons, and you're going to point and you're going to go no, yes, maybe. Can we all do that together? Start over on your left. No, yes, maybe. Say it out loud. No, yes, maybe. And again, no, yes, maybe. And one more time, no, yes, maybe. Those are the rules we use to determine if the zeros are significant or meaningful. Last day we discussed the zeros on the left, which are no, they are not significant. They're just placeholders telling you your number has not started yet. If you did not watch the video yet, you'll get a better explanation of why, okay, in yesterday's video. So these ones, no, they are not significant. So we can say no, no, no. The 5 and the 8 are significant. Now, zeros in the middle, what answer do we have in the middle? Are they significant? Yes. They are significant. So we also have yes, yes. And then finally, the 0 on the right, that is a maybe. Okay, and the maybe, we have to ask ourselves a question. We have to ask, is there a decimal? In the number? Okay. So for this one, we say, is there a decimal? How about in this one? Is there a decimal in this number? I'll draw it bigger so you can see it. The answer is yes. So when we say decimal yes, what that means is significant. Is that digit significant? That 0 at the end on the right? Yes. So yes to decimal, yes to significant. If we say decimal no, so if we ask, is there a decimal, and we had some other number, maybe like 3,700, and there's no decimal in that number, so if we say decimal no, then we would say, are these zeros on the right significant? Maybe. Is there a decimal? No. So significant. No. Okay, so that's just a really brief introduction to how to count your significant figures. We will be working with them. Hi. For Claire, yes, absolutely. So I don't know which version she would like, so I will send both of them and she can just choose which one she wants. Okay, so this one is what I call the enriched version. It has nothing in the little blanks. Okay. This one you get a little bonus mark. This one you get a bonus mark. I see. This one has some things filled in, so if she wants to do that one, very nice. She doesn't lose anything, right? Sounds good. Yeah. Okay, so if we were to count our significant figures in this number up here, we would look and we would say decimal, yes. So is this 0 on the right significant? Yes. So if we counted our significant figures, we would have 1, 2, 3, 4, 5, 6 significant figures. And we could also write that as 6 sig figs. All right, so those are our sig figs, because sometimes writing significant figures is just too long. Sometimes I'm even lazier than that, and I will just write 6SF. That also means 6 significant figures. Okay? In this number here, these are non-zero digits. 3 is not a 0, 7 is not a 0, so that is, the 3 is significant, the 0 is, the 7 is significant. Zeros on the right, remember it's no. What's in the middle? Yes, and what's on the right? Maybe. So we are on a maybe. Yes, these ones are maybe. And what do you ask yourself when it's maybe? You ask yourself, is there a decimal? Is there a decimal? No. So no decimal. Therefore, it is not significant. So this number, this one is no, these are not significant. So this would only have 2 sig figs. Now, if you've not done significant figures in physics, and this is seeming like a little bit rushed to you, don't worry, we have like an entire section where we just look at counting sig figs, but I wanted to make sure you knew how to count them before we start scientific notation, which is what we are doing today. So we are going to go back here, and we're going to learn about scientific notation. Scientific notation is always written in the following format. You will always have a number at the start. That number is called the mantissa, or actually more commonly, it is called the coefficient. Okay? I just like the word mantissa, so I thought I would put it in there. But if you want to call it coefficient, that's good. It also includes the times sign, you know, the little X for times. And finally, it includes 10 to the power of something. Okay, so that is the format for scientific notation. So we need the mantissa or the coefficient, we need a time sign, and then we need a power of 10. When you are writing this, please use a time sign and not a dot to write your scientific notation, because dots, depending on who's writing them, have a tendency to look like decimals, okay? And sometimes I have difficulty telling what students mean if they use a dot, okay? So would it be okay to write that number as 3.86 times 10 to the 6? Is that okay? No. Okay, please use a time sign instead of a dot. Now, the rule for scientific notation is that in the coefficient, in the mantissa, there has to be one, but only one, no more than one and only one non-zero digit in front of the decimal. So in this case, our non-zero digit in front of the decimal is a 3. We could not write 0.86 times 10 to the 4. This would not be scientific notation. Not scientific notation, because you cannot have a 0 in front of the decimal. It has to be a single digit between 1 and 9.99999. Okay? So you'll either have a 1 or a 2 or a 3 or a 4 or 5, 6, 7, 8, 9 in front of the decimal. So the mantissa, or the coefficient, will be somewhere between 1 and 9.999. Now, how do we figure out what our power of 10 will be? Well, our power of 10, that's our exponent, it's going to be the number of places that we move the decimal, and we'll practice moving the decimal very shortly, okay? So the number of places that you move the decimal will end up being the exponent. If we are dealing with a large number, that is, if the number is greater than 1 is what counts as a large number here, the exponent will be positive. So if we had 347, our power of 10 would be 10 to the something positive. If we have a small number, and in this case that means less than 1, the exponent will be negative. So small numbers, it would be times 10 to the negative 3 times 10 to the negative 7 times 10 to the negative something. So large numbers, the exponent is positive. Small numbers, the exponent is negative. Now the rules don't make a lot of sense out of context, so let's get down to some examples so you can see how this really works. Okay? All of this is written down for you, but I like, showing you the process as we go. So I'm going to write it here. If I had to put a decimal in this number, I would put it here. And remember, the first thing about scientific notation we learned is that we need to have one non-zero digit in front of the decimal. Right now we have 1, 2, 3, 4, 5 digits in front of the decimal. That is not okay. All right, so we are going to move that decimal place 1, 2, 3, 4 places. So instead of having 45,000, we will now have 4.5. Now I would like these two numbers to be equal. And it should be quite obvious that 45,000 is not the same as 4.5, right? Those are two very different numbers. So what we need in order to make it equal is we need the times, and then the 10, and then we need a power for the 10. We moved the decimal place 1, 2, 3, 4 places to the left. And that means our power of 10 is going to be 4. Then we ask ourselves, is this number large? In other words, greater than 1? Or is it small? In other words, less than 1. Is that a large number or a small number? That is a large number. 45,000 is bigger than 1. So it is large, and therefore we need our exponent to be positive. Anytime you have a large number, the exponent will be positive. So we just leave it like that, 4.5 times 10 to the 4. Now let's prove to ourselves that we actually have two things which are equal to each other. So if we go down here, we have 4.5 times 10 to the 4. Okay, and what that really means is 4.5 times 10 times 10 times 10 times 10, 4 times. Now 10 times 10 times 10 times 10 is 10,000. And 4.5 times 10,000 is 45,000. And if you don't believe it, punch it in on your calculator and you will see that indeed it is. So what we had, 4.5 times 10 to the 4, is equal to the number that we started with, 45,000. Is good? Okay. Now we're going to talk a little bit about sig figs, because our original number, 45,000, remember, non-zero digits are significant. So the 4 is significant, the 5 is significant. Now we have some zeros which are to the right. And remember, zeros, no. In the middle, yes. On the right, maybe. So maybe these are significant. What do we ask ourselves to determine if they are significant? Is there a decimal? Is there a decimal? No. Are those zeros significant? And the answer is no. So if there's no decimal, they are not significant. So that means they are not significant. So how many significant figures do we have? Just 2, okay? 2 sig figs. So 45,000 without a decimal in it has 2 sig figs. And that means when you write your number, even though it could be really tempting, right? We moved our decimal place 1, 2, 3, 4 places over. It would be really tempting to write it as 4.5000. How many significant figures are in 4.5000? Well, if we have 4.5000, now we look at those zeros on the right. Remember, it goes, everyone with me? No, put your arm out to the side. No. Yes. Maybe. Where are we at right now? Where are those zeros? They're in the maybe category. And what do we ask ourselves when it's maybe? Is there a decimal? And in this case, is there a decimal? Yes. It is right there. I want that in green. So yes, there is a decimal. So are those zeros significant? And the answer is yes. If I were to look at this number and I said, how many significant figures? Non-zero digits are always significant. And then these zeros, there is a decimal, so the zeros are significant, so these ones are. So that would be 1, 2, 3, 4, 5. This number here would have 5 sig figs. You must be consistent between the number you are given and the number that you find. So if you are given 2 sig figs, your answer must have 2 sig figs. If I give you 3 sig figs, your answer must have 3 sig figs. So in our question, if we go back to our question, The question was 45,000. Yes, and that had only 2 sig figs. So if I gave you 2 choices for an answer, one of which was 4.5 times 10 to the 4, and one of which was 4.5000 times 10 to the 4, which of those 2 would be the correct answer? The first one, 1, 2 sig figs. This one has 1, 2, 3, 4, 5 sig figs. This one would be correct, and this one would be wrong. Okay? Like I said, if you're not quite getting the sig fig thing yet, don't worry about it. We're doing a little learning in context, and then we're going to hit hard on it next week. Okay? And if you already know them, you'll just breeze through this. Let's just say 5. Anyway, put a big star there so I remember to change it. Okay. In our second example, we have 3750. We need to move the decimal so there is 1 non-zero digit in front of the decimal. Before we start, how many significant figures would be in this number? 3 sig figs, because no decimal, that 0 on the right is not significant. So 3 sig figs. 1, 2, 3, and that one is no. So we're going to move our decimal from here 1, 2, 3 places, 1, 2, 3 places to the left. So we end up with 3.75. Should I have 3.75 or should I have 3.750? I started with 3 sig figs. I need to finish with 3 sig figs, and because there is a decimal in this number, that last 0 is significant. Decimal, yes. 0 on the right, significant, yes. So this would have 4 sig figs. This one would have only 3 sig figs. So this one is correct and this one would be wrong. Okay? Now, that's our coefficient. What else do we need in scientific notation? We need times 10 to the something. And we moved our decimal place 3 places. So the number up top is going to be a 3. We have to decide, should that be a positive 3 or should it be a negative 3? Is 3750 a large number or is it a small number? Is it greater than 1 or is it less than 1? It is greater than 1. It is a large number there, therefore the exponent should be positive. And so we just leave it as it is. Okay, 3.75 times 10 to the 3. You can feel free to fill in the blanks as you choose. I don't know. I always think that I need more scaffolding than I do, but at any rate, what it really means, of course, we can check this out again. Does this 3.75 times 10 to the 3 actually equal 3750? Well, 3.75 times 10 to the 3 really equals 3.75 times 10 times 10 times 10, 3 tens times each other, which is 3.75 times 1,000, which is 3,750, which is the number that we started with. Hooray! Okay. This is just a bigger number. I'm not sure we need one more example, but we're going to do it anyway. Here's our number. We move our decimal place. Whoa. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is a large number. Therefore, we need to have a positive exponent. So this will then become 5.8, and none of the zeros because there was no decimal in the original number, so there were only 2 sig figs. 5.8 times 10 to the 5. Shortcut. Sometimes you've got lots and lots of zeros. Just make it easier for yourself rather than going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Like that gets kind of messy and complicated. You can shortcut by counting in groups of 3. So you would say 3, 6, 9, and then you have 10, 11 to get it beside the 2. So that would be 2.96 with a single digit, which is not 0 in front of the decimal, times 10 to the 11. And that is a large number, so it would be positive 11. Let's try counting this next one by 3s. 3, 6, and then we have to do one more. So that's going to be 7. That is 7.2 times 10 to the 7. One last one, counting by 3s. We move our decimal. 3, 6, 9. Oh, now we have one number in front of the decimal. 3, 6, 9. That's perfect. 9.3 times 10 to the, and we moved it 9 places. And it's a big number, so our exponent is positive. How are we doing? Making sense? Yeah? Okay, cool. Special case, okay? This is where it gets a little weird. So if you haven't been paying attention up till now because you already know scientific notation, you might want to wake up your brain because this one is a little strange, okay? So if we have a number 4.6 and Ms. Spence says to you, please write this number in scientific notation, well, A, it's kind of a weird thing to do because it's just so beautiful as it is in non-scientific notation, but let's say you needed to. This would be 4.6, because the decimal's already in the right place, we haven't had to move it, times 10 to the what? Times 10 to the 0. You can say, there's 2 ways to think about it. You can say, I did not move my decimal place. Therefore, how many places did I move it? I moved it 0 places, so my exponent is 0. The other way to think about it is, what is anything to the 0th power? 1. So that's going to be 4.6 times 1, which is of course equal to 4.6. Okay? But if you were asked to write that number in scientific notation, you would actually need to write it as 4.6 times 10 to the 0. So special case there. Special case number 2. When we have just a 10, just a regular 10, okay? So in this case, we are going to move our decimal place. So there's one non-zero digit in front of the decimal. So we end up with 8.34 And sometimes people are like, oh, I'm just going to write times 10 because that, of course, is equal to 83.4. However, if there is no power with the 10, that is not actually scientific notation, okay? Scientific notation requires a power on the 10. And you might ask yourself, well, what power should I put on there? 8.34. If I just want to multiply it by 10, that would be 10 to the 1, which makes sense because how many places did we move our decimal? Just one place, okay? So this would be correct. This would be wrong. I mean, not that the statement's wrong, but it would not be correct scientific notation. Okay? Small numbers. Small numbers are those numbers which are less than 1. So we were dealing before with numbers that are bigger than 1. Now we're dealing with numbers that are smaller than 1. So we're going to have some 0.00 stuff going on. But once again, we're not doing anything really differently until we get to the exponent. We are still moving our decimal until there's one non-zero digit. So in this case, we have to move the decimal to the right 1, 2, 3, 4 places. 1, 2, 3, 4. So now we have 7.6, and it will be times 10 to the, because we moved it 4 places, it's going to be a 4. However, this is a small number, yes? It is less than 1. Therefore, what should our exponent be? The exponent should be negative. So instead of just regular 4, we have to make it a negative 4. Shall we prove to ourselves that that worked? Let's go do that. So here we have 7.6 times 10 to the negative 4. And if you remember, 10 to the negative 4 is the same as 1 over 10 to the positive 4. Okay? And 10 to the positive 4 is, of course, 10 times 10 times 10 times 10. Okay? And now, so now we have 7.6 divided by 10 times 10 times 10 times 10, which is 7.6 divided by 10,000. And if you don't believe it, you can punch it in on your calculator. 7.6 divided by 10,000 works out to 0.00076, which is exactly what our original number was. Okay, so those two things are indeed equal. Zero 0.049. Oh, by the way, we should look at sig figs here too. These zeros, are they on the left, are they in the middle, or are they on the right? Those are zeros on the left. So are they significant? Are they no, not significant, yes, significant, or maybe significant? Remember, NIM. Do it with me again. What's over here? No. Yes. Maybe. Once again. No. Yes. Maybe. What are these ones? These are no. Not significant. So we can say that's not significant, that's not significant. 4 and 9 are non-zero digits. So this number has 2 figs. We need to move our decimal, so we have 1 non-zero digit in front of the decimal, so we move it 1 place. We move it a 2nd place. So now we're going to have 4.9 times 10 to the what? What number should we put up there? We should put a 2, okay? So it has to be a 2. But our number this time, is that a small number or a big number? That is a small number. So should our power of 10 be positive or negative? Negative. So it is going to be 4.9 times 10 to the negative 2, because it is a small number. So we have that negative sign there. And proving to ourselves once again, it really is what we thought it was. 10 to the negative 2 is the same as 1 over 10 to the positive 2. Yes, 10 to the negative 2 is the same as 1 over 10 to the positive 2. And so now we have 10 times 10 in the denominator. And 10 times 10, of course, is 100. And if we take our 4.9, which was in the numerator all the way along, and divide it by 100, we get 0.049, which is what we wanted. Hooray! Yay us. Okay. Shortcut, once again, count by 3s. Okay, so if you've got a big long, lots of zeros, instead of going 1, 2, 3, 4, 5, 6, 7, you can just go 3, 6. Oh, and that takes me to one number in front of the decimal, so that would be 5.41 times 10 to the 6. And because it is a small number, it will be negative 6. Here again, we have a small number, so our power of 10 is going to be negative. We can count by 3s. We have 3, 6, 9, and then one more makes 10. So it's 10 to the negative 10, and our coefficient would be 8.35. Class over. 150. Okay. No, 1240. 150. 150. Okay, we're good. I get confused on Fridays. Fridays mess me up a lot. All right, going backwards. This is actually easier, even, I think. 3.56 times 10 to the 3. Now, instead of saying it's a large number, therefore the exponent is positive, now we say the exponent is positive, therefore the number must be large. So what's going to happen is when you move your decimal, you must move the decimal to make the number larger. So the exponent is positive, therefore the number is large. Therefore, we move the decimal to make the number larger. Now, if you think about it, if I start moving my decimal to the left, would this be making my number larger or smaller? That would make my number smaller. Now I got like 0.036. So that makes the number smaller. That's not what we want. What we want to do is we want to move it to the right, which makes the number bigger. And because the power is 3, we move the decimal place 1, 2, 3 places. Now you'll notice in that little third place there is nothing up here, so we can put a 0 in there. So that means that our new number is 3560. We have moved our decimal place 3 places to the right. How many significant figures in 3.56? 3 sig figs. That should be easy because every time it's a non-zero digit, it is always significant. So 1, 2, 3. 1, 2, 3. So would I want my answer to be 3560, or would I, because I moved my decimal over here, would I write it as 3560 decimal? Remember, our original number was 3.56 times 10 to the 3, and we had 3 sig figs. Zeros on the right, maybe they are significant, right? A 0 on the right, maybe significant. And we ask ourselves, is there a decimal? And in the top number, the answer is no. So is that 0 significant? The answer is no. So that one is not significant, but these 3 are. So this number here would have 3 sig figs. In our second number down here, we say maybe, and we ask ourselves again, is there a decimal? And in this case, we let's say, oh, look, yes, there is. I've drawn it big and huge at the end there. So decimal, yes. So is that 0 significant? The answer is yes. So this one here would have 4 sig figs. Which one would be correct given that our original number had 3 sig figs? it would have to be the one that had 3 sig figs. So that would be our correct answer. The one that has 4 sig figs would not be correct. Okay. And like I said, if you're still struggling with the significant figures a little bit, don't worry about it. We will talk more about them next week. Okay. So this just talks about what we just talked about. Here's an example where we have a positive exponent. And if the exponent is positive, that means the number is large. In other words, it has to be greater than 1. So what we're going to do is we are going to move our decimal place so that our final number ends up being bigger than 1, which means we need to move it this way, 1, 2, and because the number is a 5, we need to move it 5 places, so that's 1, 2, 3, 4, 5. 3, 4, 5. Where there are gaps, you fill in zeros, 0, 0, 0. Okay, so our final number in standard notation, not in scientific notation, in standard notation will be 427, 0, 0, 0. And don't put a decimal on the end because we only want to have 3 sig figs, because our original number had only 3 sig figs. Is good? How are we doing? Thumbs up, thumbs down, thumbs in the middle. Okay, good. Let's see if we have anything else left today. This is just keeping the sig figs the same. So here we have 3.960 times 10 to the 7, and we have that decimal right there. So that means that the 0 on the right is significant because we have a decimal. So if we count our digits, we have 1, 2, 3, 4 sig figs. Now here's the problem. If we're going to move our decimal, 3.960, we go 1, 2, 3, 4, 5, 6, 7. Throw in those extra zeros there. Now, I could write this number as 3.960, 0, 0, 0, or sorry, there's no decimal there. I moved the decimal. 396, 0, 0, 0, 0, 0. Whew. How many sig figs are in that number? Only 3, because there's no decimal. So we do not count the zeros on the right. So we only have 3 sig figs. And that's not good because how many sig figs do we want in our answer? We want to have 4 sig figs. Well, what if I throw my decimal in there? Does that fix things for us? So if I write 396, and there's 5 zeros, 1, 2, 3, 4, 5. What if I put my decimal there? That's where it is, right? Does that fix it for us? Now how many sig figs do we have? Oh, good Lord. We have 1, 2, 3, 4, 5, 6, 7, 8, because that decimal makes all the zeros on the right significant. So that has 8 sig figs, and we don't want 8, we want 4. So what on earth shall we do? We're going to use a trick that is probably only going to be used in grade 11, because most of the time, if this were the case, we would write this number in scientific notation to make it really obvious that there are 4 sig figs, okay? But because this is grade 11 and we're mucking about with all the different things here, we are going to use an overbar, which is well named because it is a bar that goes over a 0. And we only use it if we're like, I don't know how to show you that this number has 4 sig figs by using a decimal or by using scientific notation. I would need to use scientific notation, but if we want to do it in standard notation, the overbar tells us that that is our last significant figure. So it indicates the last sig fig. Now, when you get out in the real world, I don't think people spend much time using overbars, okay? They would just write the number in scientific notation and be done with it. But if you need to, you can use it here. All right? Just 1 or 2 more examples and then we're done, which is good because we're almost out of time. Okay, so 3.7 times 10 to the minus 3. The exponent is negative. Therefore, we need to make the number smaller. My watch has told me it's time to take a break and move. Okay, well, we'll do that at break. So if I move my decimal place to make the number smaller, we will be moving it to the left. 1, 2, 3 places. And I need to have something go in there. So I'm going to put a 0 in there. I'm going to put a 0 in there. My decimal is going to go right here. And I need something in front of the decimal. So I'm going to put another 0 right there. So this number is now 0.0037. You should always put this 0 in front of the decimal. Yes? How many significant figures in 3.7 times 10 to the minus 3? 2 sig figs. So isn't it good that these zeros on the left, what do we say about zeros on the left? No. Okay, so no, these are not significant. So we only have 1, 2 sig figs in our answer, so that is as we would like it. Start with 2 sig figs, finish with 2 sig figs. Okay. Do we need another example, or are you feeling good? What do you think? Feeling good? All right. Homework, I will show you what it is by going to my other block here, because I wrote it all down. If you are away, watch the videos and or copy the notes, pages 68 to 70. Do page 113, the odd numbers, that is the scientific notation. There's a couple problems with the answer key, which I will put up on Teams in the general channel, and study for your accuracy and precision quiz. Again, I'll put up the details on Teams. Okay? You're welcome. Yeah. If anyone needs to either take the quiz or retake the quiz, like I said, you're welcome to come by either after school today for about 5 minutes or Monday Flex, whichever's easier. You can do it right now. Yeah. Did you want the enriched version? Yes. And if you want to do it right now, you can do that too. Hi, how you doing? Good. I'm all right. Oh, Claire? Okay.
You said I could do it right now.
Yeah.
Can I get the enriched?
Yeah.
Let's do it now.
Yep. Get it done, right?
Yeah.
Yep. Not yet, but well, they wouldn't have to bring it up. So. Yeah, it's okay. Yeah, I know. It should be on. Yeah. Watch out for this one. I don't know why she's a rough one. I can totally tell. Right? So tell. Never met this one before. I don't know what's up with her. Hi. If you want to, yeah, or you can do it after school today. Up to you. Monday? Okay, perfect. You're welcome. See you later. How you doing, Dan? Me too. I couldn't, like, my brain this morning said Saturday. All right. Oh. Yeah, my body has not accepted that today is not Saturday. It doesn't understand it.